nanoHUB.org.
Online simulation and more for nanotechnology.
So, hello everyone. My name is Gerhard, and I'd like to talk a little bit about nanoHUB and ChipsHUB, and then introduce you to our PN Junction Lab that I use for teaching semiconductor devices. So, here on nanoHUB, this is the homepage. We want to make data and simulation pervasive, so really put modeling and simulation into people's hands that normally wouldn't touch it. And we do that by providing modeling and simulation tools. We have apps that are easy to use, so not just specialized tools where you need a lot of expertise, but also we appified complex tools, and I'll give you a demo of that today. What we want to do is enable people to do use these tools and apps in research and in education. And today we'll focus on learning and teaching. And for that, we have taken several apps and combined them into a tool of tools, so to speak. And I'll talk a little bit about that. There's some of you might be developing software. And we have a framework for developing software on nanoHUB like this. And then ultimately you can share and publish your content on nanoHUB. So this is what the homepage is like, and then we have a couple of featured items. And certainly we're working on ChipsHUB as well. So chipshub.org is really a group that runs inside nanoHUB. So if you go into an empty tab and you type ChipsHUB, .org, or you can go on the link where you go to. It's a group on nanoHUB. So ChipsHUB is a subset of nanoHUB, if you will. You can really have multiple components here. So ChipsHUB is a bit more focused on semiconductor devices, while nanoHUB has a lot more items. We have a commercial Silvaco tool running right now, and we're installing Cadence and Synopsys tools. And I'll be talking a lot about this immersive learning experience that is dealing for semiconductor devices. And then we have OpenCourseWare. We have literally 170 courses on nanoHUB that have been used by millions, and we highlight several features here. And then we have free textbooks that go along with some of these new courses in the field of nanoelectronics and nanothermal. We don't do this alone. We do this with partners, and we have quite a bit of experience in doing this kind of work. And then we have resources for faculty that are in closed groups, such as homework assignments or solutions. And we're working on putting in more content into that framework. So if I now focus in on this semiconductor device fundamentals and click on here, then I go to this tool set called Abacus. And Abacus is really a tool of tools that combines multiple individual nanoHUB tools that deal with crystal structure and band model, bulk semiconductors, PN junctions, bipolar junction transistors, MOS capacitors, and MOSFETs. So this is really the topic of this recitation series. And in the past weeks, I've covered the crystal structure, band models, and bulk semiconductors. And today I'll talk a little bit about PN junctions. So each of these, topics have their own subpages with some assignments. So here if we go to PN junctions, there's a primer and some homework assignments and some exercises you can find here. And always you can click on this, run the Abacus tool suite, and what it will do, it will launch the tool. I'm already logged in, so it just launches the tool. So this is live, it's running it right now. So here is really the splash screen that you see on the screen. Here, you can always modify sort of the size of the screen depending on what platform you're running in. And so again, it's a tool of tools, and instead of having a cute little picture about the tool, we made hot links here that refer to the tool. And you can also get to the complete list of tools that are in Abacus right now. And if you can click on here, what it will do, it'll launch another tool. This one is being launched out of the in a new window. That's a newer, more modern view of PN Junction Lab, and I had fired this up here already. And PN Junction Lab actually is powered by Padre, which is a full-fledged device simulation tool that designed transistors. So here is the front end, the more modern front end of the PN Junction Lab. I'll show you the older one as well. So what you can do here is, as the screen comes up, you can actually ramp through the voltage. And as you apply a voltage, you see how the potential changes and how it's lowered on the left side. The red lines are the quasi-Fermi levels. And you can really see as you apply a positive bias, how you lower the barrier. The resulting IV looks like this. There's a CV characteristic you can look at. What's quite interesting is also to just look at the charge density here in this default example, where the dashed line is the typical textbook depletion region approximation that you find in any textbook and in any analytical expressions. So this is under a no bias. And as you ramp up the bias, you can see how the depletion region changes, and sort of a box assumption of this depletion region really starts to be not so good anymore. So, and this is the output of a real simulation engine. You can go in here. You can look at the electrostatic potential. You can look at the electric field. This is slightly asymmetric structure. So the electric field is slightly asymmetric. I can see that here in the settings. So P-type on the left is shorter than the N-type, and the doping is also different. So that gives you a bit of asymmetry. So this is fine and good. So you can actually peek into a structure and give students an idea on how the bands move. What I'd like to do next is show you something that is harder than just doing textbooks. And I peeled out something of a lecture here or a little demo. I'm going to show you a brief PowerPoint, and then I'll walk you through the live demo. So here's the former splash screen of Abacus, which looks a little nicer, but I couldn't click on it. And it's been used actually by over 19,000 users. Here's the Crystal Viewer Lab, and here's the PN Junction Lab that I just demoed. And I mentioned briefly that this tool is actually powered by Padre, this PN Junction Lab and MOSFET, etc. They literally designed transistors at Bell Labs. So it's a real tool. But if you want to use that real tool, you have to speak Padre language, which is kind of hard to learn. And if you place some commas in there at the wrong place or semicolons, etc., your simulation will fail. So you have to be a bit of an expert to do that. And the question is, what could you do in terms of if you had a real tool like this, but that would be an app that you would never do in a traditional textbook. So here I peeled out some examples when we're talking about some non-idealities of PN junctions. So here is a modern textbook by Jesus del Alamo, and you have the typical IV curve, and you have a change in the slope. And in the textbook we typically use at Purdue by Pierre, you have a similar sketch that identifies different non-ideality regions. And around these figures, you suddenly see that the prose gets very dense. And then there's some maybe verbal references or prose references to exact solutions. So let's look at some of those exact solutions, right? So I'm going to go, do not death by PowerPoint, but I'm going to go into Abacus, and I'll show you some examples. So let me go into the older version of PN Junction Lab. Still runs a little faster. It's a little bit more responsive for demos. So I'm going to make the structure here symmetric, and just put in a couple nodes, and I'm going to make the doping symmetric too. So we have symmetric doping, a symmetric physical structure, and I'm going to ramp up the voltage a little bit higher to 0.8 volts. And so I can change properties. By the way, you can look at different materials as well, and I can change the minority care lifetimes. So it's really driving a real engine. And if I hit simulate here, it'll run this configuration. And if somebody has run this before, instead of running the full-fledged tool, it should just pull it out of cache. But as you can see here, it's really running this tool. And it finished it. It's assembling the results. And here the simulation is now finished. So here I have a band edge diagram, right? That's what you might have in a textbook. And you might have an IV. And here's my IV on a linear scale. Let me put this on a log scale by clicking here. And let me make this manually. Maybe go down a little bit deeper. So here's your IV, and it has one slope, it has another slope here, right? Just like what the textbook showed you. But now you might look at some internal properties as well. So let me now look at the band edge diagram as an applied bias. So as I'm ramping up the voltage, I see what I kind of expected. We are playing a voltage, we're pulling down the barriers, the quasi-Fermi levels extend out, and at here we're at 0.4 volts or so. We start to see something interesting here. At 0.4 volts, you see a slope to develop here on the P side. And if you go to even higher voltages, you have quite a heavy slope in the band edge here on the P side, not so much on the N side. And literally, I have students run these simulations, and then they come back to me, what is this slope? Why is this? I don't see that in a textbook. And then you can have a discussion with them on this resistive type drop, and you can talk about, okay, the resistance or the mobility, and the current flow is going to be related. The current flowing is the product of mobility and the number of electrons or holes that you have, and the gradient of the Fermi levels. So obviously there's something different about electrons and holes, even though they have the same doping. So it must be something else, right? And well, it's the mobility, right? That electrons have a higher mobility than holes. So what you could do is say, okay, let me add some electrons, some holes into here, and maybe I just dope it higher by an order of magnitude. Okay, so I'm gonna now run this simulation, and if I have more holes, then I can support more current, and my resistive drop should be less. So that's my hypothesis, and I run this simulation here. And what I should see is, first of all, I should see different IV curves, and I should see different bands. So first, the tool pops up here with a band edge diagram, and clearly I made the structure asymmetric. So my charge distribution, my depletion regions, I will look different. So here is the zoomed view, or the zoomed of the net charge. And you can tell there is a different distribution of carriers here. It's asymmetric. And now let me look at the IV curve. And again, we put it on a log scale. And what I can do now is also, I have this little all button down here. I can put the two simulations on top of each other. And let me zoom in here. So you can see that when I increase the doping, I have a higher current here in this high voltage area, but in the low voltage, I don't see a whole lot difference. And we can now begin to explore that. So let's look at the bandage diagram. Let me remind you, in the case of low doping, we had looked at the bandage diagram like this. We ramped up the voltage, and then we saw a pretty big dip here on the P side compared to the N side. And in the next example, what I've done is I increased the doping by a factor of 10. And now my bandage diagram looks quite different. I almost see here, I'm going at 0.4. We already started to see a drop in the potential here on the P side. And now, even at higher voltages, I see a relatively little drop, and I see more drop here on the N side and the P side. And I increased it by a factor of 10, right? So mobility, if I remember right, for materials, looking for the mobility model in here. I don't see it. Okay. So roughly, mobility is a factor of 3 different between electrons and holes. So if I go back and just try to increase the doping here by a factor of 3, I should sort of balance out my overall potential drop. So the point is, you can start to develop some intuition. You can look at quasi-Fermi levels. I'll do that next when I begin to vary some of the intrinsic carrier lifetimes. So I just reran this for a doping 3-to-1, and I'm going to look at my bandage diagram for the last simulation. And as you can see now, both the electron side and the hole side roughly at least have similar bandage slopes. Actually, still the electron seems to be a little higher slope right now. So the next thing one can explore is, so what is this with these quasi-Fermi levels, right? So you have the electrons are here, this is the electron side, and the distance here between the conduction band and the quasi-Fermi level indicates the number of, in this case, minority carriers on the P side. But it seems like there's quite a bit of carriers still that are making it through the whole structure, but eventually they all, due to the ohmic boundary condition, are going to collapse here. So what you can do is say, what if I want to understand a little bit minority carrier lifetimes? So what if I let these carriers live a little shorter life? So they should decay faster. Maybe the material is not as clean, and there's some technical reasons sometimes why you might want to make these devices make the minority carrier lifetimes shorter for some detectors, for example. So let me just run this where I reduce the minority carrier lifetime, which means I also reduce the diffusion length. So it should change some of my quasi-Fermi levels in the device, and I should see that in my bandage diagram. So now I go in here, again, bandage diagram at applied bias. You will see that the minority carriers don't make it that far into the device on the other side anymore. So if you have a shorter lifetime, they do get injected on the other side, but they decay much faster. Right, that's some of the role, and you can sort of see the boundary conditions again here at the edges, where you collapse to quasi-Fermi levels with surface recombination at an ohmic contact. So you can do the flip side too and say, well, what if I had just where I made this really short, made the device much shorter? Let me, instead of making the device shorter, let me give this a really extremely long carrier lifetime, like 10 to minus 3. I mean, that's unrealistic, or I can make the device shorter, but this is easier to compare right now on the same scale. So I'm going to run this with a really long lifetime. So the carrier, that means the diffusion length is really long. And I should see my results really soon. Band diagram, and see the carriers really shoot all the way through until they just combine at the surface. Okay. Interestingly enough, also here then the resistive drop is changing slightly too. So we can compare these, all of these now on an IV curve. And so in the last simulation, even on a linear scale, you see you can support much more current because the carriers, the minority carriers, don't get recombined, or you had the equivalent would be to do this on a shorter device. So you can really study the various material properties and concepts in a PN junction, and you would never do that in a normal textbook. So I'm peeking to the other side, and what I had done in the PowerPoint, I basically had shown this with different screenshots. So I basically given you sort of the demo I wanted to give, at least on PN junctions here. You can do some other change. Well, we can, just for argument's sake, I made the case that instead of making the minority carrier lifetimes really long, I can also just make the device much shorter. So I can go into structure here and just make this maybe a 1 micron and 1 micron, and go back to the, I think it was 1e minus 10 seconds and 1e minus 10 seconds, and run this again. Obviously now the axes will all change because my simulation domain has changed quite a bit. So the band edge diagram is going to be a bit more challenging to view. I'm going to see if I can zoom in like this. And here you see a similar result. I made the junction much, or the PN junction much smaller. And at the lifetime that would be expected, basically all your minority carriers actually make it all the way across the device, which means it should look similar in its IV to the previous simulation. It's actually even more current because, there's a balance. I just sort of shot in the wild in terms of the thickness of the PN junction, etc. So this is sort of what I wanted to show on the PN Junction Lab. And I'd be very happy to entertain questions or show some other things that you might want to see of what might be able to be done. I will try to peek.
I can read the one question I've seen so far. Can Zeners be modeled? Zeners?
Zener diodes. I think Padre does have a tunneling model. I am not sure if it's turned on in this tool. We can try though. And then if we see Zener tunneling, good. If not, then that would be a good enhancement to be, should have not killed it all. But let me just simulate this one more time. Actually, what it should do now, load these results cached, because I had this calculated already. So if I look at these output log, this is the equivalent of the Padre input deck, except for these lines here. You would have to take it out. And I don't remember if there is a tunneling model in there. Rather than just trying, what we could do is so we have the Padre user's manual, and let me see, tunneling. Hey, look at this. Band-to-band tunneling coefficients. So it does have it in principle. So Padre, that's the fundamental answer. It could be handled. Let's see, found on 2 pages. Default is false, okay? So if we don't see a tunneling term in the input, it will not do it. And in general, I don't speak Padre per se, right? So let's see. Yeah, I don't see. I see mobility models impact. Oh, some models are saying. Let's see, interesting. So it could be a very simple fix. Because here, didn't I see impact? Yeah. So impact is set. So it does have impact ionization turn on. So it could be a very simple fix to also do Zener tunneling, except it doesn't do it right now. So I think I just we can take note and maybe enhance PN Junction Lab to actually do tunneling as well. But I hope I answered the question more or less. So the question in short is not right now.
Yeah, they said thank you, and I just made a note of that. The next person said, I wonder if it can applicate on organic FET.
Not this tool in this shape or form. Number one, this is not a FET here. This is a PN junction. I'm not sure that we have tools for organic FETs on nanoHUB. I mean, we have some 700 apps, nanoHUB. So there's course materials on it. There's compact models for organic fats, but yeah, just a compact organic compact model fat.
All right. The next question, any way of introducing statistical analysis and probability distribution of the electrons and any quantum-inspired modeling of these nano devices?
I see. So this is what I demoed today is classical drift diffusion, which is core, what we teach in the typical core. When I teach the core course as well, I do some quantum mechanical modeling and have students design a quantum dot detector in quantum dot lab. So I introduce quantum mechanics that in terms of quantum dots and confined states. And then I have them study nano wires in full quantum transport simulations. And there you can look at carrier distributions in the full tool. That is not what I've included in Abacus, but there is a tool that I use in my class as well. And this is grad level class, nanowire. This one. So here, this is a screenshot of what you get in a full quantum simulation where you have modes and you have carrier distributions in these modes and transmission coefficients, and there's actually current density. So we have some of that, and the nanowire tool is a more simpler effective mass model where you can model carrier distributions as well.
We left off with the modeling of the nano devices. So the next one, can we show reverse bias in the simulation?
Oh yeah, of course. Yeah, reverse bias is easy. So this was the short junction, I believe. So reverse bias, you just change the voltage, make it negative, and it'll run. So now you have energy band diagram on there. So now you're going in the other direction. Okay? And then the corresponding current looks like this. It just very small. And then I guess the point is, if we had the tunneling model turned on, and the doping would be harder, right? So let's do this, right? Let's do on the 19. We can do that test. We know it won't show the Zener breakdown because it's not turned on in the model, but we can at least look at the bandage diagram. And it's going to struggle a little bit more in this drift diffusion model. It runs a little longer, needed more iterations to converge. And bandage diagram. So clearly you should see Zener tunneling in this here, but the question is also, if you model this, how well resolved are the charges? Let me look at that charge density. Yeah, see, there is a ton of numerical nodes here. Yeah, that's in the reverse direction. So it looks sharp, but then seems like we can make the device much shorter. So let's make this 0.2. And then if you home in into the junction, yeah, so there definitely would be Zener tunneling in this device, and if the IV shows not much, then obviously there is no tunneling. So just like as I said, it's model isn't turned on, and it would be interesting to turn that on and have those options be available. That seems like a cool extension we could bake in.
The next one, someone asked, is the simulating software open source for academic work and teaching research purposes?
So it depends on what the authors decided, okay? So, and what the licensing agreements are. So everything on nanoHUB is open access, meaning you can get to it. Each of these tools has an about page. I didn't even highlight that today. So here, this PN Junction Lab has an about page that it's actually a proper publication. It's listed in the Web of Science. You can see there's 21,000 users that use PN Junction Lab. And this particular tool is actually closed source because Padre is not an open source engine. It's a donation that Purdue received from Bell Labs, but we're not allowed to make it open source because the authors decided not to. There's other tools like, for example, Shred. Dragica has her tool. Dragica Vasileska has her tool as open source, and you can download the open source. It's really the prerogative of the author to decide whether this tool is open source or closed source. And it depends on what the circumstances are.
All right, the next question, what is the minimum length of P or N region to simulate?
I mean, this is in a sense, a finite element type tool. PN Junction Lab is, right? What it does, it does meshing. Clearly, if you there's no per se, I presume there's ultimately a limit on how dense you can place those mesh nodes, but it's purely classical, right? PN Junction Lab. Not all tools are nanoHUB, but PN Junction Lab is a classical simulation tool. So you can actually drive it into the realm of doing subatomic or atomic length scales, but the physical result is kind of meaningless, right? If you have extremely high doping here, let's look at that. Like, let me. That would be more visible on a MOS capacitor, for example, where you have unrealistic charge confinements and you ignore the quantum mechanics. But basically, here I'm resolving the electric field, right, in these two simulations that I just ran, and you can see they're reasonably well resolved. So the peak is well resolved, and also let's look at charges. And that charge is probably a better one. Net charge density. The question is, how well are these slopes resolved here, right? And it seems like they're quite well resolved. And it's more in the other bias direction that you would worry about, I guess. So let's go here when you start to really develop these really sharp edges. And then you have to ask yourself how much of that is actually real in a classical model. Yeah, and I think the next question is, okay, so I just ran the forward bias under this extremely high doping. So here we go now, right? And it's a short device, right? So the carrier lifetime is the standard one. So you can see all the minority carriers really make it through the whole device and end up on the other side. So let's see what the net charge density looks like. And then you can ask yourself again, is this well enough resolved to be numerically reasonable? And it looks like it's placing plenty of nodes here into this junction region. And then you can ask yourself, how realistic is that? Wouldn't you want to put an intrinsic region in here for small domain where you have some mixed doping, say, where you don't have that? So you can play with these distances and number of nodes. I see the next question about various type of recombination, SRH, Auger. So we can see what's in the input deck here. Again, that could be a cool addition, right? So the models SRH are turned on, field mobility, impact ionization is on. So again, I mean, I don't speak Padre, but from what I'm seeing here is it looks like SRH is on, but we don't allow users to turn that on and off. But that could be, we could envision another model tab here, right, where you have where you turn these things on and off, including the tunneling, right? That can be done. There's not much transient analysis. The question is essentially quasi-steady analysis. I've shown, is there transient analysis in this tool? And the answer is no, not in PN Junction Lab. But so here's my invitation to you. If you had ideas of what you would show in a class with people and what you might want to simulate, we can see if Padre can. I know Padre can do not. I don't know about transient, but it might. Let's see. Find large signal. No. Okay, look, it says Padre can speak transient conditions. And certainly we can have more sophisticated tools under the hood like Silvaco tools as well, which we have on nanoHUB. I want to show a shock wave in a diode. I don't know how to do that. All
Okay,
right.
if we don't have any other questions, thank you everyone for joining us today.
Yeah, thank you, everyone. Thank you very much for coming.